Alright guys, so in this section we're going to be discussing the graphs of the other trigonometric functions. We have already talked about sine and cosine functions, so let's start with the tangent function. Okay, so if we recall our unit circle here, we're going to start just plotting some points here to kind of get the idea of the curve of the graph of the tangent function. And let's just plot some points from the unit circle here. So let's say we have an x and y here. If you recall unit circle, let's start with 0 here. So if we take tangent of 0, remember from the unit circle is y over x, tangent of 0 is going to give you 0 divided by 1, and that would be equal to 0. So I'm going to put a point right there at the origin. So tangent of 0 is 0, and again this is for the function y equals tangent of x. And let's keep plugging in more points here. What about tangent of, and let's do, so I've labeled this to be my pi halves. What about pi fourths? So what's tangent of pi fourths? So if you look at your unit circle, square root of 2 over 2 divided by square root of 2 over 2, that should give you a nice 1. And we keep going, right? What about those angles right beside, to the left and to the right, pi fourths? So like for instance, tangent of pi thirds. If you look at tangent of pi thirds, that's square root of 3 over 2 divided by 1/2. That's going to give you a square root of 3, which is about 1.73. So, you know, roughly, I'm not making this exactly, but you get the idea here. And then pi 6, you can do this similar way. Tangent of pi 6 would be the square root of 3 over 3. So that's less than 1, definitely. So, you know, I'm just going to put it somewhere in there. Now, what happens when we do tangent of pi halves, though? If we look at a unit circle, you see that the y is 1 and the x is 0. And when you do tangent, y over x, it gives you undefined because division by 0 is not defined. So then there's really nothing there for tangent. So what's going to happen here is at pi halves, you're going to have a vertical asymptote. And as it turns out, the same thing is going to happen for 3 pi halves, which is negative pi halves. You know, that's coterminal. So there's also going to be an asymptote right there. Now, if we do a little bit of the negatives in here, negative pi 4, just the same way we did positive, you're going to get similar results, but in the negative side. So it's going to be tangent of negative pi 4, so it's going to be negative 1. And soon enough, you're going to get, hopefully, the idea there. Let's try to connect. And remember, all these functions are smooth, something like that. And of course, you have an asymptote at pi halves and at negative pi halves. So then you'll get something that looks like this. Okay, kind of similar to, well, not really to the cubic function, but a cubic function doesn't have asymptotes. Right, it keeps going to infinity horizontally as well. Here, this one is restricted by pi halves and negative pi halves, but it's going to keep going up to infinity as you know, as you get closer to pi halves, and to negative infinity as you get closer to negative pi halves. Now, of course, all of these trig functions are periodic, so if you keep going to the left or to the right of these asymptotes, it turns out you're going to be repeating the same cycle here. So you're going to get another one this way, and then you'll get another one this way, and then so forth forever and ever. So you're going to have asymptotes every, if you notice here, every pi. And this is where we're going to highlight the characteristics of this tangent function. So again, we graphed a little bit of it just to get the idea, but if you keep plotting points here, you're going to repeat the same shape here, the same graph over and over again in both directions. Okay, so a few characteristics of this tangent function is that, as you can see in the graph here, this function has a period of pi, from negative pi halves to pi halves, and then it's going to keep repeating that in both directions. Also, the domain of this function is almost everything in the real line except for those asymptotes here. So again, we're going to have an infinite amount of asymptotes. We only graph one period here, but if we keep graphing this tangent line indefinitely in both directions, you know, we'll have an asymptote every pi from this pi halves, right? So the way we're going to described domain is going to be all x's not equal to wherever those asymptotes happen. So in this case, pi halves, so one way of writing this would be pi halves plus n pi, where n is just an integer. So that way, if you plug in a negative integer, you'll get the negative asymptotes here. Now the range is pretty straightforward because you see that all the y values are covered here. So then the range will be all reals, negative infinity to positive infinity. And we can also see the symmetry about the origin here, which makes it an odd function. We already knew this from before. We know that the tangent of negative x is equal to negative tangent of x. We knew that from even and odd identity. But now we can confirm that with the graph, that if you rotate this graph, we fix the origin and rotate it 180 degrees, we'll get the same graph. So this is symmetric about the origin. Okay, so similarly for cotangent of x, we have that the graph is going to be very similar to tangent x, and that they have the same period. Now they're not going to start in the same place, and the asymptotes are not going to be they're not going to be the same. Cotangent x is going to be, and again I skipped the part where we plot the points, and you can do that yourself. But once you plot a few points, you're gonna get this graph over and over again, and of course it keeps going to the right and to the left this way, and this way as well. The orientation is different too. It looks almost like a reflection of the tangent x, and it's also being shifted by half. So, but other than that, it's going to have similar characteristics. So we can see the period is still pi. We have an asymptote here at the y-axis, so x equal to 0, and also at pi, and then it'll keep repeating, going to the left and to the right? So we'll have another one, 2 pi, 3 pi, and so forth, and also in the negative direction, negative pi, negative 2 pi. So the domain is a similar idea too. We have everything, all the x's work except where those asymptotes are. Right, so then we say all x not equal to those asymptotes. And here, since the y-axis is an asymptote, n is any integer, remember, so this n equal to 0 will give you this one here, n equal to 1 will give you pi, n equal to 2, and then the negatives also in the other direction. Range is still the same as tangent. It's still all reals, negative infinity to infinity, and it's also an odd function, which we already knew. Which means it's symmetric about the origin. Right, so very similar here. You want to have an idea of the graph of these two functions. Make sure not to mix these two up, and instead of graphing point by point, make sure that you know the general graph of these parent functions. Okay, so for the cosecant function, we're going to have to recall how to graph our sine function. This is also going to be true for the secant function. So if you remember, cosecant is reciprocal of sine and secant is reciprocal of cosine. To get the graph of the cosecant function, it's going to help a lot if we graph the sine function first. Okay, so if you recall, our sine function graph looks something like this, right? Had a period of 2 pi. It went as high as 1 and as low as negative 1. So we've done this on the previous section. So let's think about the cosecant function in a more intuitive way. Remember, keep in mind that cosecant is the reciprocal of sine. If you think about sine, even go back all the way to your right triangle definition of sine. Remember how it's opposite of hypotenuse, but the hypotenuse side was never smaller than any of the other two sides, opposite or adjacent. So every time you did sine or cosine, for that matter, you did either opposite or adjacent over hypotenuse. That always gave you something less than 1, right? And after we did the unit circle and did all the other trig functions for any real number, we realized that, the range of sine was negative 1 to 1. But think about what the reciprocal would be. If sine is a ratio less than or equal to 1, then the reciprocal of it would be greater than or equal to 1. All of these values right here for sine are actually not going to exist in the cosecant, because think about each one of these numbers, you take the reciprocal of it, it's going to give you something greater than 1, except for 1 itself. And also something else to note here, and this is where we're going to get that idea of the asymptotes. Notice how all those x-intercepts here for sine, namely 0, pi, and 2 pi, if you take the reciprocal of 0, That's going to be 1 over 0, which is undefined. So then in the cosecant function, we're not going to have anything there. We'll have asymptotes there. So those zeros right there, in other words, in more general terms, they're in a section of the sine of your sine function with its midline. So not necessarily the x-axis, but the midline. In this case, it happens to be the same. The x-axis is the midline in this case, are going to be where the asymptotes are. So we have that the y-axis again is as an asymptote, and we have the pi right here would be an asymptote. And notice how I outlined the graph of the sine function just because it's not part of the cosecant. It's just going to help us graph here, give us an idea. And then I've outlined the asymptotes here, and then now I'm ready to graph the cosecant. So the cosecant is going to include 1. 1 is in there, and it's going to get closer and closer to those asymptotes, right, without ever getting there. Same thing here. All right, so that's what we call a period of the cosecant function. So just like its reciprocal sine is going to have a period of 2 pi, but then it has two parts right here, one going up and the other one going down here. They kind of look like parabolas, but they're not, because they have those asymptotes here that are keeping them from crossing to the other side. So just the stuff in blue here would be, the graph in blue would be the cosecant function. Everything else is just an aid to help you graph this function, but it's not part of the function. Now this, as any other trigonometric function, this is periodic, so it keeps going to the left and to the right indefinitely. You can keep drawing here another cycle of the cosecant function. So this is going to repeat over and over again on both directions. Okay, so a few characteristics of this cosecant function is that, as you saw, it's going to keep the same period as its reciprocal function sine. It's 2 pi, and keep in mind that so the one cycle, one period includes these two parts, right? So it's not just one of these. It's one going up, one going down. That forms one period of the cosecant function. And then we have the domain is everything except where those asymptotes happen. And notice how this coincides with the asymptotes of cotangent. If you remember here, right? They happen every pi, starting at 0, pi, 2 pi. Well, the same thing is going to happen for cosecant. So they have the same domain here as we had for cotangent. And the range is going to be everything. This goes to infinity, this goes to negative infinity, this part. So it's everything except this middle section here where the sine is, right? So that's why we have two intervals, the union of two intervals here. Negative infinity to negative 1 up to this point, union 1 to positive infinity. Also, just like the sine function, this is an odd function. The cosecant function is odd, since it's symmetric about the origin here. You can confirm that with the graph. Okay, similarly for secant, since secant is reciprocal of cosine, we're going to use the cosine function to get the graph of the secant function. Notice how I already have the cosine function graph outlined here, and then we know that the asymptotes are where that cosine function intercepts the midline, which is the x-axis in this case. And just like we did for cosecant, the secant function will look like this. It's going to be very similar. You have your asymptotes there, and then here kind of like we have this parabola looking one split in half there, but this will be just the lines in blue are what the cosecant function would be, this one cycle of it. Now of course this is 2 pi, so we're going to see that the period is still 2 pi, and we're going to have similar characteristics here. Now of course this keeps going. If we wanted to graph more, we can keep doing that. So here we have some of the characteristics of the secant function, and we have still the same period as cosine, 2 pi, and domain is going to be everything except where those asymptotes happen, which happens to coincide with the domain or the asymptotes of tangent, if you remember here, right? So tangent, we had pi halves and every pi from there on both directions. The same thing is going to happen for secant. Secant is going to have those same asymptotes. So then the domain is the same as tangent. And then the range, the same as cosecant. It's everything except all this stuff in the middle from -1 to 1. So all reals except that -1 to 1 interval. So we represent that with the union of these two intervals here. And just like cosine function is even, secant function would also be even, which means it's symmetric about the y-axis, right? So if you fix the y-axis and you reflect it about that axis, then you will have the same thing. You have the same graph. Okay, so one more thing I'd like to mention here in this section is about damped trigonometric graphs. Okay, so here in this example, we have the product of two functions here. So we have x, which is by itself is linear, and then sine of x by itself, sine of x is just a wave. But if we take the product of x times sine of x, that's going to create a new function of its own, and it's going to have a damping effect on the sine function. As a matter of fact, this x here, we call it the damping factor. So if we use a little bit of algebra here, we'll be able to see what's actually happening in the graph. So if we consider from the range of sine that we already know is -1 to 1, but that's equivalent of saying the absolute value of sine is less than or equal to 1. Now, if we multiply this whole thing by the absolute value of x, we get that the absolute value of x times the absolute value of sine of x is less than or equal to absolute value of x. Now we can do that without changing our inequality symbol, because we know the absolute value of x is going to be a positive number, so we don't have to worry about that multiplying by a negative number. Now this right here, this statement just means that I can apply now the definition of absolute value and rewrite this inequality as a double inequality here and have this. Now notice how this x times sine of x, which is our function of interest right here, is in between negative absolute value of x and positive absolute value of x. In other words, this function here that we're trying to figure out, it's going to be right in between these two, and these two functions we know how they look like. Okay, so if we graph absolute value of x and negative absolute value of x, we're going to get something like this, right? We're going to get our v shape and our inverted v shape here representing these two functions. Now the other two, and then we can plug some points and actually verify this, but I think you're going to get the idea here. Since this x sine of x is being squeezed, so to speak, by the other two, you're going to get something that looks like this. The idea is that this absolute value functions are kind of squeezing this x times sine of x function, so that this wave gets this damping effect here, hence the name damped trigonometric graphs. Okay, in the same way, we have this example here of f of x equal to e to the x times sine of 4x. We can apply the same idea here, where the range of sine is between -1 and 1. So if we multiply this whole inequality by e to the x, and we can do that because e to the x is a function that is always positive, so it's okay to do this without changing our inequality symbol. So once we do that and apply the definition, just by definition of absolute value, we can get this double inequality where our function of interest here is being squeezed by these two exponential functions. So if we were to graph these, we have e to the x and negative e to the x. So our function here, e to the x times sine of 4x, is going to have the same sort of damping effect here. And it's going to keep approaching 0 as it gets squeezed by these two exponential functions. Okay, so here we have two examples of damped trigonometric graphs, and I just wanted to have a quick word about them because they happen to have really nice applications in the real world, especially in the science and engineering fields.